a mass, M1 of 8 kilograms, is being pulled up a ramp at a constant speed. Is that M1? Yep, that's going to be 1. So it's going to be 8 kilograms. 8 kilograms. 8,000 grams. Constant speed. This means that force, net force, equals 0, which means the acceleration, net, also equals 0. By a rope that passes over a pulley and is then tied to the top of a second mass, M2, which is 12 kilograms, 12 kg. Initially, the distance between the bottom of the second mass and the ground is 1.5 meters. 1.5 meters. The ramp's angle of inclination is 25 degrees. 25 degrees. And has an unknown coefficient of friction, mu k. Okay, so there is friction. So I'm going to do it this way. Force friction. And just as kind of a side note here, since we know that the net force going, so we know the constant speed going up, net force going up is 0, acceleration is 0, so that means the forces will balance. And so what's happening here is friction is pulling it backwards, but the gravity from the other block is pulling it upward, and those will perfectly balance each other. That's why we're mentioned that there's a coefficient of friction. Okay, so what is the total work done by gravity on the two blocks as mass 2 drops the distance of 1.5 meters? Okay, so let's see. We're going to do, this is a good summation symbol. I'm going to do work on block 1 plus work on block 2. Work on block, I'm going to start with 2 because that's probably the easiest. So work is integral f dot dr. These are both vectors. That's a dot product. But since force is constant and in line with r, so motion is this way, force is this way. This will be force times distance, which will be force is mass times acceleration. In this case, will be mass times gravity. So it'll be 12 times 9.8 times distance, which is 1.5. Mass times, okay, yep. So I should probably actually calculate that out. Click, clear, 12 times 9.8, I don't know, 108, 117, oh yeah, times 1.5, 176. So 176.4, okay? And so, okay, so now we have to look at M1, which is going to be a little bit more challenging. So we have, I'm going to draw another picture up here with a triangle, like so. Purple, purple. So this, I'm going to get a bunch of colors here. This will be M1, and motion is this direction. I'm going to call that R. But gravity is this direction. So we have work equals integral f dot dr. So if you remember from calculus and math and such, the mnemonic I use is A cross B. It would make sense if that was AB cosine of theta, because cross product, cosine, same letter, alliteration. No, it's a trap. That's actually sine. And that means then that A dot B is AB cosine of theta. So cosine goes with the dot product, not the cross product. These are vectors here, vector, vector. These will be magnitudes. Lots of lines, lots of absolute value signs, symbols. So what we got here then is you can think of A dot B as how much of A is in the direction of B times the magnitude of B. And so what we have here then is when we decompose this gravity, we're going to decompose gravity like this. And so what we have here then is this portion of the right there, this portion of force gravity is going to interact with this displacement r. So specifically in this case, we're going to look at this. I'm going to call this FGX, maybe. So FGX will be FG sine of theta. Now you can figure this out using geometry and going through and finding how this theta applies to this force gravity going down. The way I remember it is a sliding block is sine of theta. I just use the alliteration between sine and sliding. And so that's how I just memorize this. You can drive it, and I like to drive a lot of things in life, but it's nuanced and complicated enough that if in the heat of the moment during a testing timed evolution, there's a good chance you're going to make a mistake. So you're better off just memorizing mnemonic, sliding block, sine of theta, sliding, sine. So that's how I do it. But then also, these two aren't aligned with each other. Well, okay, they are aligned, but theta in this case doesn't equal 0, it equals pi, or if you prefer degrees, 180. And so what we're going to have here then is just going to be FG sine of theta, FG sine of theta, where we're talking about this theta right here, times distance, I'm going to call that delta x, and then times a -1, because it's the displacement is opposite from the force due to gravity. Okay, so basically what it's saying is that the tension in the string is overcoming the force of gravity. So looking at this in a little bit more detail, we will have force of gravity will be mg sine of theta. So mass is 8. Did we say 8? I'm pretty sure we said 8. So we have 8 times, wait a sec, what do we got here? 8 times gravity, which is 9.81. I'll just leave it as 9.8. Sine of 25. Times -1. No, times the distance traveled, which will be 1.5 meters, times -1. Okay, so that's I think probably the most correct, most formal way of looking at how to do this. Another way that would be to look at this, which is probably the way I would do if I was stressed for time here, is I know gravity operates up and down. And so I would just look at everything in terms of up and down. So you're like, all right, this block drops 1.5 meters. So that's going to be, so work equals mass times acceleration times distance. So that would be mass, which would be 12 times 9.8 times 1.5. Okay, now this block, it's actually going upward. And it's going upward. So this will be 2, this will be 1. It would still be mass times acceleration times distance. Mass is 8. Acceleration is 9.8. But it doesn't go up 1.5 meters because it's at an angle. We're going to do the sine here. So that'd be 1.5 times the sine of 25. And if you look at it, these are actually the same setups we have for both of them. So one of the things to take into account here then, or to think about, is the first time we did it, we aligned everything to up and down. We aligned it to the ramp's coordinate plane. The second time when I kind of winged it, so to speak, I aligned everything to the up and down vertical, aligned everything with gravity. So this 1.5 sine of 25, what I'm doing is I'm shortening the distance it traveled because it traveled up. On this case over here, what I did was I basically shortened the force, the gravity, by sine of 25. And so I had a smaller force but a greater distance. Either way you look at it, the numbers all come out the same. So, long story short, we'll take these two, subtract one from the other, and that will give us our total work. And we already discussed over here why they're supposed to oppose one another. And thinking in terms of going up and down, mass 2 goes down, mass 1 goes up, but gravity is always down, so these two numbers are going to have to oppose each other. Okay. Ooh. I know I calculated earlier, but there's a lot of stuff that I might be able to factor out here. So I'm going to do 9.8, which is, I think, gravity. We have 1.5, which is the distance traveled. And we'll do 12 minus 8 sine of 25. Nice. I like that. All right. I'm going to calculate that out real quick. Get the calculator. Pow. On. Clear. Mode. Degrees. Click. Second quit. All right. So we'll do 9.8 times 1.5 times quantity. 12 minus 8 times sine of 25, and that's assumed to be degrees. And I'll close the parentheses for both the sine and the overall, and I get 126.7. Wow, that's a lot of zeros. 126.7. And this is in work, so it'll be measured in joules. 126.7, is that something? No. I'm going to call it this one. 126 to round it. Yeah, I'm good. Okay. So answer will be C. Total work done by gravity is 126.7. And your first thoughts at this point is like, wow, that took you like 10 minutes. And you don't have time to do that, take that much time. You're right. First time I go through this, go for maximum understanding, because when you're working through homework problems, you shouldn't be in a rush. I know you're always in a rush. We're all in a rush in life, but try and take your time and understand what's going on. On a test, I would probably go with this method of just sort of winging it. The mass 2 goes down this far, under this much, with this much force acting on it. Mass 1 goes up this far, with this much force acting on it in the opposite direction. The signs should oppose each other. Answer. And that's much quicker, but you really don't have the safety net of a logical, reasoned, step-by-step progression through the problem. So that's how I would approach it for both an evolution and a homework scenario. Okay, focus. What is the total work done by all forces on block 1 as mass 2 drops a distance of 1.5 meters? Interesting. Okay. So this one is a bit challenging. So we're going to look at this from a conceptual point of view. So we got a ramp like so. We have a block, mass 1, and it moves upward. So work is joules, change in energy, conversion of kinetic to potential, or potential to kinetic. And so it's being pulled up the ramp. And so there are two forces here. We have force friction and a tension, which is basically going to be due to gravity on the other block. So it doesn't really matter where this second force comes from. We just know there's some force pulling it upward. And so we're going to look at this as work. I'm going to call this total, which is the same as saying work net, which will be the integral of all the forces times the displacement. And so what we know then is the force net, force total, sum of the forces, is 0 because it's a constant speed. Another way to see that is through the kinematic equations. So if you look at the kinematic equations real quick, A equals constant, V equals AT plus V naught, X equals 1/2 AT squared plus V naught T. So a constant speed, this means V final, this equation right here, V final equals V initial for all given time, assuming time isn't constant. That means that A, in this case, this part right there, has to equal 0. So that constant speed is telling us that we have a net acceleration of 0, which is going to give us a net force of 0, or a total force of 0. So this is going to be 0. Your first thought, like your spider senses should be going crazy at this point. The reason that, so you're thinking that, all right, this block moved up, it obviously gained potential energy. The potential energy at this point is obviously higher than potential energy at that point. If a mass fell on me from this height, it would hurt more than if it fell on me from that height. Therefore, it has more potential energy. It has more energy due to its position in the universe. It's mass times gravity times height, approximately, if you will. And that's a good intuition, but there's some unaccounted, even though it gains energy, it has effectively lost energy due to this friction. Now, I understand energy is never lost, but as it's going up the ramp, there's enough of a scratching and interference and interaction between the block and the ramp, generating heat, I don't know, maybe deformation, some sound, energy that's not being used, that's being removed from the block's kinetic energy. That energy lost is compensating for the energy gained by moving up in height. So you gain some energy by moving higher, but it also loses some energy due to friction. And the net result for this is no work is actually done. So you could say work is done by gravity pulling it up, work is done by the friction holding it down, but when their powers combine, they cancel each other out. So the total work done by all forces on the block is mass M2. Ooh, I was looking at M1. Okay, it drops a distance of 1.5. Okay, so I'm going to look at this again slightly, but I'm pretty sure all my arguments still work. So mass 1, we already determined, moves at a constant speed. Well, okay, they told us that, which means it has 0 acceleration, which means force, net forces is 0. And so since it's attached by a rope to mass 2, therefore they're moving together in conjunction with each other. It's not like mass 2 can move faster or slower than mass 1. I guess it could if you kind of crinkled the rope, but the idea is they're moving together. So the only difference between what I explained earlier for mass 1 and mass 2 is for mass 1 I said, all right, we're losing energy due to friction. With mass 2 you'd say, well, we're losing energy due to this mysterious tension of the rope pulling up. But that tension is connected to block 1, which is ultimately due to friction. So everything I said about mass 1 applies to mass 2. Therefore, mass 2 also has a total work done of 0. Yep. Now again, when you're doing this sort of thing on a test, you should immediately think, all right, constant speed, acceleration 0, no work's being done. Most likely. That should be your feelings and intuition. All right, what is the tension of the rope? Okay, so we don't actually have to find a value. We just have to find if it's greater than or equal to mass 2 times gravity. Okay, so when we think of tension, we think of a force, which is a mass times acceleration. And acceleration on, in this case, is going to be gravity. So the force on block 2 due to gravity will be m2 times g. So this right here is gravity. So if we do ourselves the free body diagram, we have block number 2. We have force due to gravity. Yep, draw a little bit higher. And tension. Therefore, at this point, we can look at these. And we know, okay. So we know from our previous discussion here that it's going at a constant speed. Constant speed means acceleration equals 0, which means force net also equals 0. And the only way we can get a net force of 0 based on this free body diagram is if force gravity equals force due to the tension, or maybe just tension. And so we're going to have answer B. tension equals mass 2 times gravity. So this is a really good problem. It's really good to understand what's going on. I'd recommend, if you get a chance, to go through a block and do all the geometry required to prove that the force of gravity going down in the x direction, down that direction, is force of gravity times sine of theta. Just do it once to kind of prove that, okay, that feels right, and then just memorize that the force of the block sliding is mass times gravity times sine of theta, sine for sliding. After that, there's a lot of talking about work. So work equals integral f dot dr. Hopefully you've had an exposure to integrals at this point, or at least dot products. If not, well then kind of go with it. Work, the big idea here is that work is the force in the same direction as the displacement. In this case, displacement is either d or r or x. And then we talked about forces balancing out, and the implications of constant speed. Implication of constant speed is acceleration is 0. We can see that through our kinematic equations. And the second one the way I write it up. And then from that, we got our answers. So hope that helped. I will see you on the next problem. A block with mass m equals 4 kilograms released from rest at the top of a frictionless inclined plane. The initial height of the block is h. The block slides down the inclined plane and then along a rough horizontal surface. Okay. For a distance of L equals 0.4 meters. Okay, so L is 0.4 meters. At which point it compresses a spring. The spring has a spring constant of 45 newtons per meter, and the spring distance is 0.15. So I probably write 0.4 here. Is that the proportion? No, it should be. No, I think these should be bigger. From equilibrium. The entire horizontal surface, including the part under the spring, has coefficient of friction UK. All right, so there's going to be friction under the block as it's sliding for a total distance of 0.55 meters. So that's important. What is the height of the ramp? Okay, so this is just conservation of energy. So whenever you think of conservation of energy, you think energy kinetic initial plus energy potential initial equals energy kinetic final plus energy potential final. Now, this is more useful for when you're talking about things that are frictionless. So what's going to happen here is we've got a whole bunch of potential energy. It slides down this frictionless plane right here. It's converted all the potential energy, EP, with 0. We're going to assume it starts from rest. There we go. Therefore, that means that the initial kinetic energy is 0. We can find energy potential, comes down. We're going to call this a 0 height, and therefore the potential energy, mass times gravity at its height, will be 0 at the end, and we've converted a whole bunch of potential energy to kinetic energy. Then we lose energy along here due to friction, this rough kind of thumpity thump, 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 as this block goes along this rough path. It then hits the spring, which then adds an additional braking and a bigger loss of energy. So what we're going to do is we're going to find out how much energy is lost here. We're then going to say that that amount of energy is the same as energy potential at the top. We could convert that to energy kinetic and then convert that energy kinetic all the way up to energy potential, but since we know they're all the same, so this is energy loss to friction and spring. To friction and spring. So we can find this. Therefore, we could, if we wanted, we could find the energy kinetic, how fast it's moving at the bottom, and then we could find out how much potential energy it had, mass times gravity times height, at the top of the ramp. But we're going to skip the middle part because we know equals equals equals. We'll find the friction and spring loss and equate that to potential energy at the beginning. Okay, so let's check look at this part. So energy lost due to friction. So work equals F dot dr integral. This is going to be due to friction. And so the block is going this direction. So this will be the displacement direction. But friction is acting this direction. So we're going to get some sort of negative number. And they're in line with each other. So the cosine dot product, cosine will be, actually the cosine will be 180 or pi, which will give us -1, but they're in line. So this will be equal to negative f times distance traveled. In this case will be 0.55, L plus the compression, L plus D. Whoop, L plus D. Now we're going to have to do work of the spring, which will be, now even though part of the friction and part of the spring happen together, we can separate them this way for this problem. So F dot dr integral, the force for a spring equals K dx, where dx is the displacement from the beginning. So this is going to be something like kx dx. I converted the r to the x. They're both displacements. And what you get is you factor the k out because it's a constant. You get x squared over 2. I already did the integral. Yep, and so you get 1/2 kx squared is the traditional way that you write the energy due to a spring. And it's just an integral of the force caused by a spring. Okay, so now when we combine these two, when their powers combine, if you will, so we have this and that. I know my notation is terrible. Keep the concept in mind and worry a little bit less about the notation. Ooh. I didn't mention what this force was. This force will be mass times gravity times mu k. So force due to friction is normal force, and since it's a flat surface, this will be mg. If it was a not flat surface, I think it would probably be like mg cosine of theta. But since it's flat, theta is 0. Mg cosine of theta is therefore just mg. So we got delta x. Okay, so we have work total will be mass times gravity times mu k. And then, as I said, here this delta x is L plus D plus and 1/2 k, and this compression of the spring will be d squared. And you notice here that the friction has to do with mass. So whenever you see, these look different because this one has mass, this one doesn't have mass, and that should kind of set off warning alarms in your head that these just don't seem to match up. Well, it's okay in this case because the energy lost due to friction does rely on the mass. If you think of it, you have friction, harder than something is being squished down, the more resistance is going to have to be pushed. While with the spring, it's all due to the compression of the spring and has nothing to do with how big the mass is. Now, if you have a bigger mass rolling down a hill running into a spring, that'll of course compress the spring more, but that's more the conversion of potential energy into the spring, not the actual work the spring is doing on its own. So you should feel kind of uneasy that there's no mass here, but it's correct. All right, so let's see if we can, I don't think we can even, can I factor anything out? I don't know, I don't think I can. All right, so I'm just gonna throw in numbers. So we got a mass of 4, so 4 times 9.8 times pi 0.2, yep, 0.2, and then this is gonna be 0.2 plus 0.4 plus 0.15, which I'm going to write as 0.55. 0.55 plus 1/2, and then K, I think it was 45. Yep, 45 newtons per meter times D, which is 0.15. 0.15, and then we square that. And this will then tell us this will be the amount of energy lost from the bottom of the ramp, and this will be equal then to mass times gravity times height, where height is what we want for the ramp. So solving that real quick, we can divide that whole thing by mass, which is 4 times 9.8, and that will give us height of the ramp. Okay? Giant calculator crunch. I'm always worried when I put a lot of numbers in a calculator that I'm going to make some mistake. Worries me greatly. 4 times 9.8 times 0.2 times 0.55 plus 0.5, which is the same as 1/2, times 45 times 0.15 squared. It gives us an answer. Divide by quantity, 4 times 9.8, close, 1.23, 0.123, 0.123 meters. Okay, so we got 1.123, and that's even a possible answer, which is nice. So to backtrack a little quick, see what we did here. We start with energy potential up here, converts to energy kinetic down here, energy potential, converts to energy kinetic. That energy kinetic is worn off with friction, which was mass times gravity, normal force, times mu k, times the distance traveled. And we had to make sure we included the distance it traveled while being compressed on the spring. And we also factored in how much energy was lost due to the spring compressing. So we could find how much energy was lost and then transfer that into energy up the ramp. What is the work done by the spring as it stops the block? I think we already found that out. What is the work done by the spring as it stops the block? So work equals integral f dot dr, which we found this is kx, probably negative k delta x, which gives us 1/2 k delta x squared, which is 1/2 times 45 times 0.15 squared, which is 0.5 times 45 times 0.15 squared. And it'll be 0.506. 0.506. And then these are all negative, so we don't have to worry about the sign here. Yep, that's right. And I think it is going to be negative because the motion, so since it's f dot dx, these are both vectors, force is towards the ramp, so force will be this direction, the displacement is that direction, and since the force and direction oppose each other, we'll get a negative. I dropped that, I should not have. Okay, yeah, that's kind of interesting because it makes you question if there's an easier way to do this that I skipped because we already completely answered that question, like right here. That was that whole point of that term. Oh well, I'm sure it's not a big deal. Maybe it is, I don't know. Suspicious. If a block with 1/2 the mass, 2 kilos raised from the top of the ramp, the distance that it compresses the spring would be, okay, so we're basically asked to do a completely new problem, but we have this equation right here, which we're going to leverage. So, this part, I'm going to say then equals mass times gravity times height. So this is the loss due to friction, this is the spring compression, and that is the height of the block. So to solve this, and this is assuming, this would actually probably be difficult to solve because D here would give us a quadratic. I don't want to solve a quadratic, but everything here is written in terms of a value, 0.075. So what I'm going to do is I'm going to plug in 0.075 and then see what kind of h it gives us. So I'm going to replace 0.15 with half the value, 0.075. And if it gives us a lower, higher, or the same h, then we can kind of figure out how much energy is required there. Yep, we're going to do it that way. So we're going to, we're going to say 2, because this is the new mass, times 9.8 times 0.2 times, and this will be 0.4 plus 0.075, because this is really L plus D, plus 1/2 45, because it's the same spring, so it'll be the same spring constant, times 0.075 quantity squared, all over 2, because that's our new mass, times 9.8. Now it'll give us the amount of height required to compress the spring, 0.075. Yep, I'm good with this. So we'll do 2 times 9.8 times 0.2 times quantity, 9.8, 0.2 times 0.4 plus 0.075. Make sure my zeros are good. Okay, at least good enough. Plus 0.5 times 45 times 0.075 squared. Okay, divided by 2, divided by 9.8, and we get 0.101. Okay, so what this is saying is this would require to compress the spring for a mass of 0.2 to compress the spring a distance of 0.075, it would require a ramp of height. Ramp is the other direction. 0.101 meters. Well, more contrast. Before we had a ramp of, what we actually have is a ramp of 0.123 meters. And so, therefore, since we have the extra energy, 0.22 meters worth of extra energy, we are going to be able to compress the spring more than 0.075 meters. Block of 1/2 the mass was released from the top of the ramp. The distance that it compresses the spring would be, greater than 0.075 meters. Okay, so let me go through the logic of what I did real quick. So we already came up with an equation with how high the ramp had to be based on all these factors. We then used that to find out the height of our ramp. We were then asked a question, a very oddly specific question. It's like, all right, we have a block that's half the mass, and ask, all right, will it compress the spring greater than or less than this semi-arbitrary number that they give us? And when we could figure out how much that spring would be compressed, but it gets challenging because of this d right here. Because this d is squared when you have the energy of the spring, but it's also, I guess, not linear, not squared to the first in terms of friction, because it's not only compressing the spring, but as the spring moves, it also loses energy due to friction. And that would give us a quadratic, and I don't want to do a quadratic. And so what I did was I plugged in the number 0.075, and I figured out, okay, instead of finding out how far the spring is compressed, how high of a ramp would we need to compress it this much? And we found out that we'd need a ramp that's 0.101 meters. And we know that we already have a ramp that's 0.123, so the current ramp we have is more than sufficient to compress this spring 0.075 meters. So it'll compress the spring more than that, and that means that we would use that it compresses the spring would be larger than 0.075. So that's a pretty tricky question, and to actually solve it in a more methodical way, rather than relying on intuition and such a specific answer possibilities, would be kind of challenging. So that's it for today. I hope this helps. I will see you next time.